different USRPs and each of them have their own individual RF channels, will I be able to do a MIMO on this? The answer is yes and no. Yes, because you will actually be able to connect these two USRPs to a single computer and in fact access them from a single piece of code, and you will be able to send the channels respective information. So here you will be sending S1, here you'll be sending S2 in the first time period. Here you can send minus S2 star, and over here you can say send S1 star. So it's basic programming that you can do in order to achieve this. But the problem occurs is that these two USRPs are not synchronized. Now I've been using the term synchronized with you since yesterday, and I have not explained to you the exact meaning. That's what I'm going to be doing to you today. What do I mean when I say they are not synchronized? Do I mean that the cable length is different? Do I mean that the signal itself has to have, so when you look at protocols like I2C or any, you can take any serial protocol, you usually have a clock associated with it, which allows the synchronization. Do I mean this? What exactly do I mean by synchronization? I'll be telling you. There are two different meanings when you say synchronization. One, I'll be explaining to you now with the picture of the hardware that you just saw. And the second, I will come to when I come to the PXI chassis system. So with respect to the first meaning, now if you look at the USRP, let me just share the presentation that has an image that will make a lot of sense right now. So here, if you see, I told you that the actual carrier frequency is generated by pure PLL plus VCO, which is correct. The output of your PLL plus VCO will be giving you a carrier signal, which will then be multiplied to your I and your Q. If you remember from the IQ architecture, we have two separate streams of data before they are combined and sent to the RF port. Now, so the PLL plus VCO does the actual generation of the carrier signal. But what we'll have to remember is that the PLL plus VCO cannot on its own, as a RF circuit, it cannot on its own generate a signal from scratch. It needs some sort of reference to do that. So a PLL plus VCO can understand that it's supposed to multiply the frequency of a certain signal. It knows how to multiply, it knows how to divide. But the PLL plus VCO system does not know how to actually generate a signal of a particular frequency. So what we have to do is, since this doesn't know how to generate a signal of its own. So if I say 10 megahertz, it can't do it of its own. So in order to facilitate it to work in the way it's supposed to, what we do is, it's not shown in this diagram, but there is actually something called as a clock reference that we give from here. So you have actually inside your USRP, you have a crystal sitting in where it is capable of providing a certain, basically not levels, it's basically capable of producing a signal that looks like a clock signal, which we call as the frequency reference signal. Typically in a USRP, in USRPs, the clock signal reference is 10 megahertz. Now, like I said, when we came to those IQ impairments where I said you have different DC offset, the mixers have different gain. Similarly, in different USRPs, you have different crystals, and each crystal does not produce exactly precisely 10 megahertz. There may be a crystal that produces 10.0001 megahertz. There may be a crystal that actually produces exactly 10 megahertz, so on and so forth. So what happens is, when I try to transmit a signal from two different USRPs, and I try to do a MIMO signal from two different USRPs, the carrier frequency generated here and here are different. So firstly, your signals won't mix. So if you remember, STVC is made in such a way that even though they mix, and actually they're supposed to mix, that you use that mixture, the fact that it mixes, you use that fact in order to demodulate and decode your channel data in your receiver. But if it is of different frequencies, that mixing procedure does not happen properly. Meaning when you're trying to demodulate, you will have different amounts of phase. So if you look at a constellation diagram, so if I provide an example of a constellation diagram, if your phase is off, I've told you that instead of the QPSK signal looking proper, like a proper square like this is how a QPSK signal is supposed to look. It will look rotated like this. If there is a shift in frequency, it will keep on rotating. Here you only have an angle. If the phase is not right, a signal will only give you a particular angle. It will stay at that angle at all times. But if there is a change in frequency, then this keeps on rotating. So if you see any constellation that looks like a spokes of a wheel, then that means that there is some sort of frequency mismatch that is happening. And in this case, there is a very good chance that this frequency mismatch happens. The second issue that occurs is that if you look at this again, there is an ADC and a D. There are DACs and ADCs present over here. Now, obviously, each of these USRPs has their own ADCs and DACs, and even those need a reference, a clock reference, because an ADC is what you basically sample out data, right? So DACs and ADCs basically take out samples of data and either convert it from digital to analog or analog to digital. Now, let's take an ADC for an example. So let's say my sample period is like this. This may be for USRP1. But the problem is in USRP2, the sampling might start like this. You can see that there is very clearly a phase mismatch between the samples that I take. And this also doesn't do us any good because your signal processing just goes all over the place when you try to do this. So in order to get around this, because even let's say I'm taking a Rio also, but I want to do a 8x8 and not a 4x4 or a 2x2. That time I have no choice but to have multiple USRPs. But because of this problem where you have different clocks and different references in each USRP, you are not able to get a system that is very accurate. So what NI has done is they have made a product called as an Octo Clock. An Octo Clock has multiple ports in it, 8 to be exact, 8 ports called as ref in. The ref in is the reference, ref out. The ref out is the reference that we give for a local oscillator or a PLL plus VCO combination. PLL plus VCO is given a wire from this one port. So let's say I have USRP number 1. So I have USRP1 and it has a local oscillator over here. The wire over here, reference is connected from one of the ref in wires. There are 8. We can connect one to this. The second USRP, again, the local oscillator's wire can be connected over here. Now, why this works is because this Octo Clock contains a single crystal. The crystal in the Octo Clock is again not perfect. It is not ideal. But since both the USRPs get the exact same reference, it is able to maintain the same clock rate and generate the same carrier frequency. Similarly, there is something called as a Pps Output, which is the reference that we provide for the ADCs and the DACs. So the references go like this over here. In a single Octo Clock, we'll be able to connect 8 USRPs. So you can imagine that we'll actually be able to build a pretty big system, like a proper base station to mobile station transmitter receiver system, when we have a Octo Clock present with us. Now, an image of an Octo Clock, the Octo Clock actually looks something like this. You see, it says 10 megahertz outputs. This is for the first 8 that you see over here is for your clock outputs, and the rest of them are clock PPS outputs. You can also connect multiple Octo Clocks together. You see something called as PPS input and 10 megahertz input. So let's say I don't want 8, but I want 16 output ports. So in that case, you take 2 Octo Clocks. Over there, what we do is when we use 2 Octo Clocks, we use a master-slave scenario. Meaning one of the Octo Clocks is the one that will actually be generating all of the 10 megahertz, that is a reference signal and the PPS signal. And the other Octo Clock will simply take that signal, multiply it across many outputs. And when I say multiply, I mean replicate. The same thing it takes in, it does all of the power operations that it needs to do, power splitting and all of that. And then after that, it gives the same output over here. Now we don't have just 8, we have 16. So in this way, in fact, even if you see NI's demonstrations in all those industrial presentations that they give, they actually show a huge system. They show a 128 antenna system and everything. And they use octo clocks like these. They don't actually use these octo clocks. There is actually a step higher where you have a lot more precision for the ones that they use. But the general, concept is still remains the same. You basically use one clock source in order to do all of that operation, all of those operations. This is with respect to octo clocks. Anybody has any doubts in this? Okay, if not, I'll move on to what I was talking about yesterday, right? So yesterday I was talking about the PXI chassis system. Just to recap, a chassis system is something that will allow us to have multiple. It has slots in it, which allows us to take data from multiple data acquisition cards that are there. There are ports inside which properly fit with the data acquisition cards that are there. And it's not just one type. So it doesn't, if I put a, say, a temperature data collection card, so which is basically an analog input card, it doesn't mean that I always have to put analog input out here. I can actually put a digital input also. I can put a digital output also, so on and so forth. This has a single interface that connects with whatever system that you're working on. Depending on what type of chassis that you buy, you will either have to directly connect this to your system, as in any data that comes from this will be properly routed, synchronized, and sent to your system. Or you can actually have a processor controller system on your chassis itself. These are called embedded chassis, where the controller in the system will actually simulate a computer, meaning this is not required at all. You just buy the chassis, you have to buy the data acquisition cards, and then that's it. The controller comes along with the chassis. You have USB ports, some of them have display ports, some of them have HDMI ports. So you will actually be able to connect monitors to this, connect keyboard and mouses to this, and work with this as though it's a computer without having an external PC that does all of the work for you. Now, an example, or rather a use case of why we would need this in an RF case would be, like I said yesterday, let's say we have multiple USRP RIOs. The first use case would be that a single normal this thing that's there, your CPU that's there, does not have all that many X8 PXI slots. We need something called as an X8 PXI slot, which would look something of this sort. It needs a minimum of X8 slot for one particular USRP, because what happens is we connect something called as a card over here, a PCIe card, which contains the Fpga on it. So the Fpga, in a sense, sits inside your computer, and the Fpga is outside the USRP. In a USRP RIO, the Fpga is outside the USRP box. It sits inside the PCI slot in your computer. In a normal host-only USRP where you can't program the Fpga is inside your this thing itself, your USRP itself. Now, that is one reason, since you can't connect multiple of them to the same system. In a PXI system, you actually have slots. You have something called as MXI card slots, where you just place in these cards. You have ports in those cards. You then connect them to your USRP. Now, I told you that there are two things I said when I meant synchronization. One of them was, I just showed you what it means. It means that you have you give some reference to your USRP so that your both your carrier frequency that you generate from the local oscillator as well as the ADC sampling that you do, ADC DAC sampling that you do is correct. Now, there is another type of synchronization that is required, which actually you may be familiar with, called as hardware triggers. Now, what we actually do, or rather most of the work that we do, would be in the software called as LabVIEW. So let's say I say turn on USRP 1, turn on USRP 2, turn on USRP 3. So let's say I'm working with 3 USRP simultaneously for some reason. Let's say I'm doing some sort of music algorithm to determine direction of arrival or whatever. Let's say I have to work with 3 USRP RIOs at this point of time. Now, in the software, I can say turn USRP RIO all 3 of them at a time. The advantage with LabVIEW software is that you can actually inherit a good, you can actually implement a good amount of parallelism in your code. you can have two portions of a code running simultaneously without interfering with each other. Of course, all of this, if you look at your actual processor, it is not physically capable of doing parallel processing. What actually happens inside is there is a pipelining where each stage is given to each process. And you always have, so that is the type of parallelism that happens over here. True parallelism is usually only achievable in your hardware such as FPGA and these PXI systems. By the way, PXI, I've been mentioning the name, right? The system that I showed you over here where you connect multiple USRP reels, it's called as a PXI chassis system. PXI stands for PCIe. PCIe is, like I said, is a communication interface. PCIe extension for instrumentation. So that is what PXI stands for, and usually PXI systems are the ones that we use when we are talking about multiple USRPs or multiple RF hardwares. So, okay, coming back to this, let's say I'm using multiple USRPs. Now, what happens over here is, like I said, you can define that these three are happening in parallel in your software itself. But like I said, your CPU resources, your applications that are running on your desktop are always fighting for CPU resources. So usually what happens when I say parallelism is that in a very quick fashion, it will implement this, it will implement this, and then it will implement this. Now, there is a very good chance that right after it implements turn on USRP1, some Windows service could take access to the CPU, delay it for some amount of time, and then only after that USRP2 is turned on. Now, the problem that occurs in this scenario is in a lot of RF applications, synchronization between signal is absolutely essential because of things like phase. Now, like I've said, phase is a very big problem that comes up in any RF scenario you take in. Phase is a very big problem that we have to solve. So things like this, where you really can't, control what happens to the CPU, it becomes a very big issue. Now, yes, I said you have FPGAs. You can say that, okay, fine, we have FPGAs, so we can use them. The problem with FPGA is that each USRP has a dedicated FPGA to it. And inter-FPGA communication is a little tricky for us to achieve as users because there is a lot of synchronization process that we have to do. And by the way, an FPGA that you put inside a system, you'll actually have to close up your CPU system also. I said we put it inside a slot, right? This actually only when you open up your PC, you'll have to do. And it's always not best for, so since we might not have, the person who's working on this might not have expertise with respect to the physical aspects of the FPGA. Maybe they're very good with VHDL, but they're not very good at taking out which output they have to take it out at, how they're supposed to synchronize it, all of that. So that might become an issue, and it's best not to tinker with it on a hardware level. It's okay if we do it at a software level, but especially a USRP FPGA card, the inputs and outputs are predefined, and it's usually best not to tinker with it. So what we do in this scenario is, in the software itself, we write a piece of code that says have hardware triggers. Now, I mentioned that the PXI system has cards where your MXI cards go over here, your PXI chassis system. If you look at the back of this system, there are actually a couple of lines that are running, which are called as trigger lines. Meaning, I can say that once this USRP starts, trigger these other USRPs using the hardware and then make them start running. So there is no code that I have to write to switch on USRP 2 and 3 explicitly. I can just say switch it on when the trigger says OK. So at this point, I can actually switch on all of these USRPs. I'm just giving switch on as an example. You can do a lot more things with triggers, but I'm just giving switch on as an example. So when you do this, you'll actually be able to achieve a very good level of synchronization between your USRPs. So if you want to, and this is actually extremely important, especially when you go to things like massive MIMO and 5G, where you have just so many antennas that are there and you have to synchronize all of them. Hardware triggers are an absolute necessity. You will have to have them. And this is the place where your PXI systems come into play. PXI systems are very useful in these scenarios. This is with respect to how they work with USRPs as such. There are, of course, USRP is not the only piece of hardware that RF hardware that NI makes. NI makes a lot more hardware. So I'm going to talk about one other system that's there. Before I do, anybody has any doubts, any clarifications? Okay, if not, I move on to the next piece of hardware. Now, this was with respect to the PXI system. Now, a PXI system, the one that I mentioned to you, PXI is in term, it's a general term. The one that I showed you right now, the one where I talked about MXI cards, is NI, if I'm not wrong, 9021. This is the PXI system that has MXI slots where you can actually buy the MXI cards, connect all of your USRPs that are there. Now, like I said, this is just one among many. There is another PXI system that I've actually worked with that I can talk to you about. I worked on this for a project extensively. And it's also on RF hardware, but it's not USRP, or rather independently on its own, it's not a USRP based one, but you can of course connect a USRP to this. That is called an NI. Second, I can actually show you the image of this. Yeah, this is the one that I'm talking about. It's called an NI5668. As you can see, this is actually the chassis itself is not shown here. This is how the chassis would look like. Yeah, sorry, this is how the chassis would look like over here. So the chassis comes with 3 components in it. The 5668 chassis comes with 3 components. The one that you see on the right over here is something called as a synthesizer. It is NI5653. It's called as a synthesizer, where basically this does the exact same thing as that of an octo clock. It generates a local oscillator reference signal. You see that there are some wires going in over here. This wire gives the local oscillator input from the 5653 to something known as the down converter. Now, if you notice what I mentioned, NI hardware, or rather NI USRPs, are not capable of going above 6 gigahertz. There is only one piece of NI hardware which is capable of transmitting at 7.2 gigahertz. That is the NI export, and that's also a USRP. And this is the only USRP that has 4 RF channels in it instead of the regular 2 that you find in Rios. But obviously, when you want to do things like 5G research, or at least on the receiver end, if you want to do any 5G research, you will be very limited when you choose USRPs, because they are not capable of, since the transmitter is also like that, the receivers are also not capable of going beyond 6 gigahertz. In order to get around this, NI makes receivers, again, there are no NI-RF hardwares that go beyond 7.2, but there are receivers that go up to 26.5 gigahertz. Now, this is useful for things like spurious signal detection, record and playback systems, etc. I've actually used it for a project. I'll explain to you what I did in the project. So this is a system that is capable of receiving up to 26.5, and in fact the lower frequency is also pretty low. It is from, you can see over here that it's from 20 to 26.5 gigahertz, 20 hertz, so which is a pretty low signal, pretty low frequency. So what this does is, this is a down converter system where it takes in the whatever input that you give. So you have an RF input over here. This could be a wire, it could be an antenna, it can be anything. So whatever comes in, it takes that signal, down converts it to what we set it to. So this doesn't directly give us the baseband signal. What it does is it down converts this into an IF signal. An IF signal to a frequency where we will be able to actually process it. So let's say, for example, there is some signal that's supposed to come in at 20 gigahertz. Obviously, our USRPs cannot take in that 20 gigahertz. What we can do is, we can give the signal to this 5606. It's the down converter is called 5606. You can give it to this. You can set the IF frequency in this to say 1 gigahertz. And obviously your USRP is capable of taking that 1 gigahertz. So you down convert it to that intermediate frequency, and then you give it to your USRP, where your USRP will do all of the necessary calculations. Suppose you don't want the USRP, you want to directly use this as a down converter and get digital signals from this. that is also possible. The thing is, this particular unit that you see over here is not capable of doing that. So right next to this, when you get a 5668, the entire chassis, you will also get another unit along with this called the 5624, NI 5624 that you see over here. What the 5624 does is, it takes in the analog input, it has ADCs inside it. It takes the analog input, gives it to its own ADC, and then it gives out that value as a digitized value. You will actually get a digital signal from this, which similar to USRP, you can take onto your system and then do whatever signal processing you want. The system that I worked with had the synthesizer, which gave the local oscillator signal. It had the 5606, which was the down converter, but we did not use the digitizer simply because we directly gave this to a USRP. We actually needn't have done that. We could have directly gotten it, but there was a reason why we did it. So the project that we were working on had specs there. Okay, so I'll explain to you what the project actually was. Project was that we were to take in a signal that was whose bandwidth would go up to 100, actually not 100, 160 megahertz. Bandwidth should go up to 160 megahertz, which your USRP radios are actually capable of. Your 2954 and 2955 USRPs are capable of going up to 160 megahertz analog bandwidth. We were supposed to take this bandwidth and we were supposed to record it, as in record it on the system as a file, and simultaneously play it back in the L band. So why do we need to do this? What is the application of this? An example would be a defense one, where you would have to be in the border and you will receive spurious signals from, say, some other country from that is in the border. What you could do is you could, of course, immediately you'll not be able to do all of the signal processing and understand what they're doing, right? So what they do is they collect the frequency at a higher band, they convert it to a band that they are comfortable with, and then what they do is they retransmit it to another location where it will be processed. Right now, if required, they'll even store it over here for later. And at the same time, they'll also retransmit it to another location in a band that they're comfortable in. And then they will analyze, do all the analysis at that end. Suppose the receiver missed this, there is always the backup that we put in the file over here. So that is what a record and playback system is. Now, the reason why we didn't use the digitizer over here on the 5668, but we used a USRP radio. The one we used was 2954. There were two reasons. One reason was that this required a GPS tag along with it. I'm not quite sure if this has a GPS tag on it. Okay, I know 5668 does not have a GPS tag on it. So they required the GPS tag, as in from which location are they receiving this and which location are they transmitting it to. Those information they needed. Followed by, they also had a specification saying that we want the ADC to be a 14-bit one. But the 5668 digitizer was a 12-bit one, which is why instead of sending it to the digitizer, we sent it to our USRP RIO over here. The RIO converted it sent it to the PC that was there. And then the PC recorded it and then simultaneously allowed the RIO to play it back in the L band. This was the project that we did, and this is the chassis that we used. Of course, in a record and playback system, we're not doing a lot of things, so we didn't have to use any triggers in the back over here. But there are triggers are present in this in case you want to use them for any application whatsoever. Any doubts in this? Okay. If not, then I'd like to move on to the last piece of NI hardware that I had prepared for this session, which is actually a pretty interesting one called as a radar target simulator. Now, obviously, everybody knows what radar is. It stands for radio detection and ranging, and it is something that will allow us to detect not only the presence but also the location and exact distance of a particular object. Radar's applications, of course, it ranges from simple a car detecting another car on the road to you actually detecting enemy military aircraft, their distance, their position, and whether or not they're approaching. Now, a radar system, actually radar systems, I'll just give a very brief on what radar systems are, followed by I'll tell you a little bit about the hardware as well. Now, a radar system can go from 3 megahertz to 300 gigahertz, depending on the application that we actually have at hand. 3 megahertz actually falls under the HF, it's the starting frequency of your HF, and 300 gigahertz is the larger one, where actually you have different applications for different frequency ranges that are there. Now, the 3 megahertz one is usually used for large distance. So if you have, say, an enemy aircraft detection up to the range would go up to around 200 kilometers for this. So if you have any enemy aircraft that is coming in along your border, this would actually be a very good system in order to detect whether they're there or not. And of course, the 300 gigahertz one is used for shorter distances, such as detecting the speed and the position of, say, a car on the road. It's only capable of doing it up to a few meters. So we really can't rely on this for enemy aircraft detection. Now, why are there different frequencies? There are a lot of reasons that are present for this. You can talk about it from something called as range resolution. So in radar, there's a concept called as range resolution, where let's say I'm using a 3 megahertz high frequency output. I have a ball over here, and then I have another ball, which is say 3 meters from this ball. A high frequency system will not be able to detect the difference in distance between this ball and this ball because the resolution is less. Whereas a 300 gigahertz radar system will actually be able to detect this small change in distance. The formula goes like this. Of course, before I go on to that, radars, as you might know, there are many different types of radars. You have something called as pulsed radars, which send out bursts of signals. It's not continuous. So it's something like, oh, okay, you send it like this, and then you give some quiet time, and then you send another burst of signal, and again a quiet time. Now, you have also things like continuous radar systems, where you continuously send a pulse and then receive it. You have systems called as chirps, where you actually sweep across the frequency. You don't send it in one frequency. You send it in one frequency, immediately switch to a slightly higher frequency, and then immediately again switch to a higher frequency, so on and so forth. So there are different types of radars. The one I'm talking about actually works for the one where you send bursts of it. Now, the range resolution of a radar is given by a common formula, that is C, which is the speed of light, into pulse width, how wide is this pulse, divided by 2. Now, why do we have to care about why a pulse is wide? It really depends on your application and how far you're expecting your signal to go and come back, how far you're expecting the object to be. So if your object is farther away, then you can use longer bursts. Why do you want longer bursts? Simply because as your radar's range increases, your signal has to travel farther back and forth. And as we know, wireless signals degrade very fast over distances. So if you have a larger pulse width signal, then it is capable of traveling and coming back. Or rather, let me put it in a better way. Whether it's a short pulse or a large pulse, they'll be going through the same channel and coming back. So that won't really affect us. But the probability of us detecting a larger signal, and by larger signal, I mean a longer signal, is more than the probability of us detecting a smaller signal. A smaller signal would of course help if the distance is lesser, but a larger pulse width is used when the distance is larger. To give a very brief on how a radar system is, or rather a block diagram, a very primitive block diagram of how a radar system is that you have certain specific terms when it comes to radar. It's not exactly the same as what you would see in a normal wireless communication system. You have first something called as a digital waveform generator, which does all of your waveform generations in the format that you want. You want it as a pulse, as a chirp, as continuous, whatever we need. It gives that in the digital format. Usually sitting inside here is an FPGA. 99% it's an FPGA. It might be controlled by a host, but it's definitely an FPGA. Followed by which you have an ADC, which of course converts the digital analog to, sorry, not ADC, my bad, DAC, which converts the digital to analog. And then you have a set of filters. So you have a two-stage filtering process where you have a bandpass filter, you have an amplifier over here, and then a mixer which mixes it to the correct local oscillator frequency that you want. So let's say I want to do it at 3 gigahertz. This provides 3 gigahertz, and then the signal again goes out. You have another bandpass filtering stage which band limits your signal, followed by another transmit amplifier over here. So this is a power amplifier. It amplifies your signal. Before going to the antenna, it actually goes through a circulator. And then it goes to the antenna. Why a circulator? Because as you know, a radar system not only transmits but also has to receive the signal simultaneously. And you don't want the transmitted signal and the reflected signal to combine in any way. So what we do is we put in a circulator over here. So if a signal comes from the transmitter, it directly goes to the antenna. And if it comes from the antenna, it then directly goes to your receiver. In the receiver, is the exact same thing, except that you have the reverse process exactly of what's going on here. And remember, we take it from the exact local oscillator that is present over here. We take the mixer local oscillator signal exactly from the same point. Again, because we would want it to be, we don't want it to be unsynchronized. We would like to make sure that the reference for both of these are the same. And since we are taking it from the same local oscillator itself, there really shouldn't be any problem of frequency, carrier frequency offset over here. Suppose this, you have an ADC, and then it goes to your digital waveform generator. Where you have all of your signal processing and whatnot. You basically have everything that you require. Now, in a radar system, if you look at it, so ideally how we would want the radar system to work is, if you look at the timeline, let's say I'm sending a radar pulse like this. This is your T, this is your power. Now I would send a radar pulse like this. I would wait for some amount of time, and then I would wait for some amount of time, and then I would receive a response something like this. Now notice two things. First of all, the power obviously would be lesser, but this is an ideal case what I've drawn over here. An actual radar system's pulse will look like this. Because you not only have your targets, but also other things like trees. You have some amount of interfering signals because of your local broadcast channels that are there, mobile signals, radio, whatnot, because all of them come under the same range. I said it starts from 3 mega, right? Your FM also starts around your FM is also around 80 mega also. So there's a very good chance that interference happens over here. So, and you have a lot of these unwanted signals that are coming in, noise that comes in, all of that. So what they do is the very easy thing that we can do, and the very primitive thing that is done, is that you set a threshold for this. You say that unless a signal is bigger than this value, ignore it. Which works well with respect to this. But again, I don't want to delve into too much depth into this, but there are a lot of other things that need to be tuned and set when you're actually operating a radar, and it needs to be done in a continuous fashion, simply because your environment keeps on changing. You can't expect your environment to be exactly the same. It keeps on changing, which is why, at least in the beginning, you always had to have a radar operator expert who had to sit with the radar system. You might have seen this, I don't know, in some television show or something, where you actually have operators sitting on the radar at all times and then doing it. Before, how it used to be is the operator not only had to see and understand what the radar was telling them, they also had to tune it in a very fine way, in an expert way, in order to make the radar a useful system. Basically, without an expert radar operator, original radar systems were useless because they would not give you the correct output that you wanted. Now, of course, with the advent of things like AI, machine learning, statistical models, etc., your radar systems are actually they're becoming into something called as, or rather, the development of radar system is moving more towards something called as cognitive radar, where you have systems that are not only taking in signals but also learning and adapting from them. So the cycle would go something like this. You have your environment over here. The signal would come in. The AI system would then sense it. First, of course, it has to sense. and then it will learn, and then it will adapt itself depending on this, and then it again asks for the environment, or rather sends a burst of radar signals into the environment, and the process keeps repeating itself. So as it operates, a radar system will keep learning on its own. So at this point, what happens is when you have such radars, the operator need not be that actively involved in the radar system. So instead of trying to tune the radar system, the operator can, of course, even now an operator is absolutely required. You cannot just leave a radar system on its own and expect it to detect and alert us. You will require an operator, but the operator at this point can focus on understanding what the signal is telling us rather than trying to tune the signal to what we wanted to tell us. So their work has reduced, and it's made their lives also easier, and it's actually made even more accurate predictions with these models that are coming in. Now, one thing that is there, so let's say, let me take an example of where I and a friend of mine are learning game of chess. So let's say my friend is an expert and I don't know anything about chess. So I start learning about it. So as I keep playing more and more matches, I keep getting better and better. But the problem with AI systems is this, the exact same thing happens in an AI system as well. But how would you say that, okay, fine. How would you say that at one point, okay, Raghavendra plays well. He's played these many matches. So right now he plays well. How would you say that? You would probably play a match against me, see how I perform in that match, and then depending on how I do, you'd say either I'm good at chess or I'm bad at chess. Now, this you'll have to do a similar thing while trying to test out how this AI-based radar system works. And remember, this, like I said, this AI-based radar system keeps learning on the go. Meaning, if I perform a test today and that test goes well, that does not necessarily mean that tomorrow also that test will give the same result, because it could have learned, the AI system could have learned something today and it will give me a different result tomorrow. Now, in an ever-changing system like this, where it keeps changing with every single data point that it gets, how will we actually, try to understand if the AI model that I've built for this works properly or not? There is one way. One is to, build simulators that simulate all of the conditions. You check out your AI algorithm for n number of conditions and then come back. But that's a very tedious process, because in a simulator, there is only so many parameters that you can define. There are only so many things that you can do in a simulator. So this happens to be an open research problem that's there in the world right now. How would you validate a radar system, or not? I'm giving you an example of radar system, but this is for any cognitive system that's there. How would you validate its behavior on a continuous basis and understand that it's working properly or not? So this is actually an open research question. Now, right, so after all of this, so let's say you develop your radar to everything that you need to do. Finally, there's a phase called testing, right, where you try to understand if the radar that you've built actually works in the way that's intended. Not just, I'm not talking about just the continuous testing, I'm talking about at least the initial testing that you do before deployment. Now, one thing that you could say is, okay, fine, I'll take my radar system to an open ground. I'll have my environment, I'll set up my environment that there are multiple trees, buildings, and everything. I'll have a plane that's coming in like this, and then I'll test out my radar by bouncing things off the plane. This is one case, and they actually do this, but there are several problems associated with it. Firstly, it's very expensive to try and rent out an entire airfield. You would want to rather do this at the end rather than the beginning, because you would want to be absolutely sure that the money you're spending is actually giving you good valid results, and that your radar system is not underdeveloped. Second thing is, it's very time consuming. Third thing is, let's say you're doing it at 80 megahertz, your radar is at 80 megahertz. You may have local FM stations nearby that do not allow you to transmit and receive at this frequency, simply because they have their station's information and your signal could interfere with their signal. And radar systems, trust me, are extremely powerful. The power that comes out of a radar antenna is very powerful. So it can very easily interrupt or interfere with any signals of the same frequency in its vicinity. Like this, there are multiple problems that are present. So what they've come up with, and I actually a couple of other companies also come up with, is something called as a radar target simulator, which is what I wanted to talk to you about. A radar target simulator is a piece of hardware that is capable of taking in signals, radar signals. You can set this to any setting. So over here in the previous part, where I put that slide. All right, here. Okay, so over here, when you're testing it out on the field, you obviously can't test it out for every single scenario. So let's say I'm preparing my radar system rent so many things per day would be very high. And there are, of course, many other scenarios. I'm just giving you a very vague example. There are many other scenarios that you might have prepared your radar system. You would have properly coded and prepared your FPGA for any scenario that's there. But you won't be able to test out each and every scenario because of your limitations, practical limitations such as this. So in all those cases, what you do is you have a hardware called as a radar target simulator, where you will be able to code any situation that is there into the target simulator. You give in the signal to the target simulator and you take it out from there. What the target simulator does is, so let's say I am telling the target simulator, okay, fine. I want the signal to bounce off an airplane that's supposed to be 70 kilometers away. And there is a concept called as radar cross section. So when you send out a radar pulse, depending on the area, on the shape of whatever is there on the plane, a certain amount of signal is reflected back. So the area of it that reflects back the signal and the power of the signal reflected back, all of these are factored in, and it is given as a term called as radar cross section. We call it as RCS. So we can give the RCS of the plane, we can give the distance of the plane, we can give the speed of the plane. Depending on how much frequency shift is there, using Doppler effect, we'll actually be able to give the velocity of the plane as well. All of those things I can encode over here. It will actually take in the physical signal that you give from your radar system. It will do all of the processing. So how does it do the processing? I can give you a very simple example. So if it's 70 kilometers away, let's say it takes 50 microseconds for the signal to come back. So this radar target simulator will add a 50 microsecond delay and then send it out. This is a very simple example I'm giving. It does a lot more complicated things with whatever radar signals that I give, but just an example I'm giving you. If it is speed, then it will change the local oscillator, the center frequency. It will change it just slightly and then give it back. FC, it will change. And what else? RCS, it will attenuate your signal and give you. So all of these factors are taken care of inside. You have FPGA sitting inside that does all of this work for you. And I will usually give you some example codes for this. You can again hook this up to your system and do FPGA coding on this. And I usually gives examples. So simple examples you will be having with you. But the only problem with this is these systems are actually extremely expensive because firstly, it's the hardware that is involved in this is just very high level. Second thing is that all of NI's products are in US dollars. So the currency that they use because they're based in the US. So it's all in USD. So when you convert that to rupees, it actually the cost is pretty high. But this is again hardware that is present that will allow you to do a lot of things if you want to do research on radar target simulators. And one other thing is that even though these things are expensive, they are a single time investment that you will have to do. If you want to rent, you can only rent out an airfield. You can't buy it. That will be a lot more expensive. So compared to that, if you do a one-time investment, you can actually keep on using this for whatever research that you're doing. And you will actually be able to simulate targets on a real time. And you can, if you have a specific situation in mind that you want to code, you can also actually code that on your radar target simulator and then test out your this thing that's there, your radar system that's there. Usually, from your radar system to your RTS, they connect it through wires simply because all of this is performed in a lab. Now, like I said, a radar system has a lot of power. So it's not really in a lab setup, at least it's not really good to put an antenna and have people moving around when the antenna is actually, throwing out all those beams. So what they do is they connect it with antennas. Suppose you want to test this along with your antenna system to see how it behaves. Then the best thing that you can do is put this inside an anechoic chamber and then do whatever antenna testing that you want to do over there. But again, usually your radar target simulators work with wires. They don't work with antennas. So antennas, if you want to have, you'll have to put it inside an anechoic chamber. With that, I think my time is done now. If there are any questions, I'd like to take it up. I just gave you a very brief on all of these so that it's not a training session as such. I just wanted all of you to be aware of what are the different NIRF hardwares that are there. So depending on your field of research or interest, if at all you get the chance to work with these, then you'll be able to know, you'll at least have a starting point as to where to start with and what products are available. That was the intent of my session. So if you have any questions at all, anything at all, please let me know.
Yes, participants, if you have any queries, you can ask now. Yes, Raghavendra, I think no queries we have. Thank you so much for the presentation.
Thank you, ma'am.
I think Nilutpal has joined.
Hello, ma'am. This is Nilotpal here.
Hello. Yeah, hello, Nilutpal.
Am I audible, ma'am? Properly?
Yes, very clearly.
Okay. Okay. When we can start the session, we can give a 5 minutes break. We can start the session after that, ma'am. That's fine.
Yeah, I think we don't need a break right now because
Okay.
hardly we started at 10 o'clock, right?
Okay.
So we can start. And how about, do you have any material to upload?
Yeah, I will
share?
share. I'll
Yeah,
share.
please try sharing it. Let me see if it is visible.
I've shared. Is it visible?
Yes, sir. It's visible now.
Okay.
Dear participants, we have